Hello, this is the first video from chapter 1424, from chapter 34 on ray optics. Last chapter we did wave optics, so we focused on properties of light that really heavily depended on the fact that it was a wave, so things like interference and diffraction. In this chapter and the next chapter, we're going to focus on ray optics, geometric, or in other words, geometric optics. And this focuses on the, more so on the particle nature of light. So some of the equations that we're going to introduce, to prove some of these equations, maybe you have to appeal to the wave nature of light. But in drawing pictures, we can just imagine that the light travel in just these rays. So you'll notice that, this chapter starts off talking about the ray model of light. And it's just saying that, look, for every object, there is light coming from it. So sunlight is hitting the top of this tree, and it scatters off, and it bounces off in all sorts of random directions. And so you can consider that top of the tree as a source of light. Not very much light is coming off, but enough to be able to see it. And so you can just draw a line from whatever source, and there's light traveling along that path. So in this video, we're going to study a couple of the basic properties about reflection and refraction. And that'll take us into something called Snell's law, so to be a little bit more quantitative about it. So that's just the path of light rays and how it can change when it strikes an interface between two media. And then as we continue on, we'll focus on a couple other properties, and we're working our way towards being able to study lenses and forming images. We can talk about prescription glasses, cameras, things like that. So we want to be able to talk about some applications of this by the end of the course. Okay, so the problem that we want to be able to answer has to do with this phenomenon called refraction. So we have to imagine we're at the bottom right corner of a pool, and our pool has a shape of a cube of side length A. So we're wondering what's the minimum angle of sunlight that will hit the bottom right-hand corner of this pool. This will involve knowing, or we'll need to know how light bends at the interface right there in order to be able to answer this question. Okay. All right. So after just introducing this, so the book is just introducing you. It's saying, by the way, we're going to focus on different properties other than waves right now. And we'll focus more on properties of ray diagrams later. So right before we talk about lenses, we'll talk about ray diagrams and apertures and all that. So we don't really need to focus on that so much right now. So we'll come back to 34.1. Okay, so I want to imagine that you have air right here and water right here. Okay, so maybe we'll draw in for the water. And remember, we already introduced the definition of index of refraction. So this is saying how much slower light travels in water versus air. So in air, the index of refraction is very close to 1. It's a little bit more than 1, but to 3 sig figs, it's 1.00. Water, though, has an index of refraction 1.33 approximately, around 4/3, not exactly, but to this level of precision. And so what that means is that light in water travels 1.33 times slower than in vacuum. So if you want the speed of light in water, you would take 3 times 10 to the 8 meters per second and divide that by 1.33. So I just want to remind you, the speed of light in a medium is the speed of light in vacuum divided by the index of refraction. Okay, so we've defined the two different media, 1 and 2, for air and water. And now we're going to draw a light ray coming down like this. Now, when the light strikes the interface, it has 2 options of what it can do. And really, it does both of these things. So some of the light will bounce right off. Oops. like that. And some of the light will continue on into the water. Okay, so the light that bounces off undergoes what's called reflection, and the light that makes it through undergoes refraction. All right. Now we're gonna have one key formula for each of these two things, one formula for reflection, one formula for refraction. It's important to keep in mind that these formula are going to refer to angles, and the angles are always with reference to the angle of incidence. So angle of incidence, angle of reflection, angle of refraction, they're all of these things are angles with respect to the normal. So this is the normal direction. In other words, it's the perpendicular direction to the interface. So all angles are going to be relative to this. So the incoming light ray, this is the incoming one. The incoming light ray has what's called an angle of incidence. So this angle of incidence, theta I, is the angle that the light is coming in at, relative to the normal, just like always. Okay, so theta I is the angle of incidence. Oops, sorry. If the light ray reflects, it'll have some angle of reflection. Okay, so theta reflection. And I'm writing out the word there because we're going to reserve the subscript r for refraction. So we're going to focus more of our attention in this video on this angle right here, theta r, theta refraction. That's going to be the more complicated formula. So theta reflection, so I'll write out the word for angle of reflection. And if the light ray makes it through, then we have an angle of refraction. But notice how all of those are with respect to the normal. So one of the main reasons students get problems wrong in this section is that they define their angles with respect to the interface rather than with respect to the normal. Okay, but all of the equations we're going to write down are going to assume angles with respect to the normal. Okay, so reflection, light will go off this way, refraction, light will go off this way. Okay, so we want to study these two cases separately. So let's look at reflection first, and then refraction second. And that'll take us to the end of this video. Okay, so the first topic, reflection. So this one's easy. You have an angle of incidence, woo, and an angle of reflection. They're equal. This angle and this angle are equal. Ugh. So maybe I even want to say, so this one's going to be different. The angle of refraction is going to be different. But the angle of reflection is equal to the angle of incidence. All right. So theta I is equal to theta reflection. Now this assumes that that the interface here is smooth. Okay, so your book mentions briefly something called diffuse reflection. That's for a rough surface. So most surfaces, if you look at just a random object in whatever room you're in, most of them aren't shiny enough so where you can see like your reflection. So what's actually going on at that interface is diffuse reflection, in which case if you look at a magnified view of the surface, it's not quite so smooth. So light coming in is reflected off in random directions, seemingly random directions. It's undergoing, this angle of reflection is equal to the angle of incidence locally, but because the surface isn't smooth, it looks like it's random. So that's why you don't see a reflection when you're looking at, say, the wall. It's because it's undergoing diffuse reflection. But for a smooth enough surface, if parallel light rays are coming in, parallel light rays are coming out. And so a clear image will form as a result of that. That's called specular reflection. So anytime I draw an interface, we're just going to assume it's smooth right here. Okay. Otherwise, it's hard to keep track of things reflecting off of it, right? So your book focuses on this a little bit more with plane mirror and virtual images. Well, images after that. Okay. I suppose actually I was going to hold off on this, but maybe it's worth going into. For a mirror, okay, so we're going to be in the habit of drawing these diagrams when we get into lenses. We're going to have diagrams representing an object. So we're going to have a mirror right here. And this is our object. And the object we're often going to symbolize with an arrow. Okay, so really any part of an object there's light coming off of it. We're just going to focus on light that's coming from the tip of the arrow right here. Right? And we're going to see what happens to that light. Okay, so let me just draw a few light rays and see what happens to that. Okay, so light from the tip of the arrow from the object. So like right here, they're talking about a tree. So I'm just going to look at the top of the tree and assume the base is right here. Okay, let's see. This light ray if it goes straight towards the mirror, it's going to bounce right back. So light ray going in, one comes out along that same direction. Okay, a light ray that goes like this, it's going to bounce off like this. So again, angle of incidence is equal to angle of reflection. Okay, so the incoming ray looks like this, the outgoing ray looks like that. Now you can draw an infinite number of these things. So another light ray would look like this, bounces off like that. There are a whole bunch of these. Now, I want you to focus on the outgoing rays. I'm going to highlight them. I'll draw them in a different color again. So this ray is coming out. This ray, remember the direction in is equal to the direction out, but it's coming out that way. And this one's coming out along this direction right here. So all that stuff looks like it came from a point right around right here. So notice how if I trace these light rays back, it looks like, if I just focus on those light rays, it looks like it's coming from right here. Okay, so really you only need to draw two of these really accurately to see where the light's coming from. But notice how it looks like, if we're looking at light that already bounced off the mirror, it looks like light is coming from here. So we call this an image. An image is where light appears to originate from. And because light doesn't actually, so I'm using a dotted lines to indicate that light doesn't actually come from here. Light doesn't actually come from here. So because the light doesn't actually come from there, this is known as a virtual image. Okay. Later on in our study, we're going to be looking at virtual images and real images. A real image is the light appears to come from there, and light does actually come from that point. Here, this is a virtual image. So imagine you're looking at a mirror. You see your reflection. You see an image of yourself on the other side of the wall. Now, if someone on the other side of the wall put their hand from, in the location of the image, light doesn't actually come from there, right? That's one sign it's a virtual image. Imagine sticking your hand at that location. Is light actually coming from there? Yes or no? So if not, you probably have a virtual image. Okay, so the procedure that we just did, where we looked at light, this involved a lot of reflection, right? Angle of incidence is equal to angle of reflection. It was all reflection. We're going to be doing this later on in the chapter and next chapter with refraction and lenses and everything. But this general procedure is called ray tracing, and we're going to learn some rules for how to do this. Okay, but for a mirror, there's a virtual image just on the opposite side as the object, and the distance here is exactly the same. So I'm not going to focus so much on the formulas that your book introduces right here. It's like this. S prime and S. We'll talk about that when we need to, when we're talking about lenses. But ray tracing, images, virtual images, I want you to get to know the lingo. Okay, so reflection problems are generally just some geometry. So for example, if you had reflection problems, this is all geometry. This just becomes like a high school geometry class. So if you had, what do I want to do here? Well, imagine you had a like a 90-degree angle right here, and you had light come in this way. So light is going to bounce off. So I'm going to imagine that the angle right here is 45 degrees and 45 degrees. If that's the case, then the light's going to bounce off this way, going to be exactly horizontal, and it'll bounce this way, and it'll emerge right here. So these light rays are going to be parallel. The incoming ray and the outgoing ray are parallel. But again, it's a lot of ray tracing. Again, it's angle of incidence, remember, relative to the normal. And here, when I was referencing these were relative to the normal, so don't forget that. So one fact that's useful to remember in these reflection problems is that if a light ray bounces twice off a right-angled mirror, the paths are parallel. The incoming and the outgoing paths are parallel. So here it's obvious from the geometry. What isn't quite so obvious is, well, what happens if the light ray is at some angle initially? You know, it's coming in like this. So then you got to be really careful about all the angles in this problem, but it turns out that the outgoing ray is going to be exactly parallel. I forgot how you symbolize this. I think it's something like that. I skipped geometry in high school, so it turns out I don't know geometry because of that. So yeah, these light rays are parallel. Even if they don't come in parallel, if they're bouncing off a right-angled mirror like that, they'll the incoming and the outgoing rays are parallel. So one problem would be prove this. You know, be careful with the angles right here. Label angles and their complements, and carry this through and show that that these two are parallel. Okay. There's not much physics with those kinds of problems. It's just geometry at that point. What's maybe more interesting for us is the refraction part. Okay, so again, we're gonna look at this light ray, and then we're gonna focus on a light ray that is able to go through. Okay, so again, we're gonna have air and water. So let me remind you that this is water right here. Water, air. So now what happens here, so this is theta incident, our angle of incidence, and this is our theta r, or angle of refraction. So what happens is that, so if you have an angle of, index of refraction n1 and index of refraction n2, if you were going from a lower to a higher index of refraction, and that's what's happening here, if you're going from air into water, the index of refraction is increasing. What happens with light rays is that they bend towards the normal. Okay, so if you're entering a higher index of refraction, you bend towards the normal. Okay. Now, what about the opposite? So we could have also drawn this light ray going the opposite way. So if light starts in the water, then all of a sudden this would become the angle of incidence rather than the angle of refraction. And this would be the angle of refraction, but it would look very, very similar. It would be, you'd come from the water and go towards the air, but in that case, the light ray bends away from the normal if you're going from a higher to a lower index of refraction. So this black line could describe either way, whether light is going from air into water or water into air. You're either bending towards or away from the normal, depending on which direction you're going. So notice your book draws exactly those two cases. So on the left here, we have from air into water, bends towards the normal. From water into air, on the right, is bending away from the normal, but it's the same exact path. You might notice also that your book describes it quantitatively. Okay, so there is an angle, there's an equation relating all of these angles. Okay, so just to clear up this picture, I'm gonna focus on this case. And actually, so I already labeled these 1 and 2. So I'm going to call this, instead of incident and refractive, I'm going to call this theta 1 and theta 2. Okay, theta 1 in index of refraction n1 and theta 2 in index of refraction n2. So in that case, what you have is something called Snell's law. n1 sine theta 1 is equal to n2 sine theta 2. So it's not quite as simple as the angle of reflection is equal to the angle of incidence like before. When a light ray refracts, so by the way, this is all under the heading of refraction. When a light ray refracts, like we said before, if n increases, theta is going to decrease, right? If compared to n1, if n2 gets bigger, then theta 2 has to get smaller to compensate for that, right? So sine is a monotonic function from 0 to 90 degrees. And so theta 2 decreasing and sine theta 2 decreasing are the same thing. Okay. So the reason for this is, by the way, so in order to prove this, you would use the fact that the frequencies are the same. So if you're going to draw the wave crests here, the wavelength in water is going to decrease. Okay, these wave crests are going to get closer and closer together in water, and as a result, you kind of need to shrink how far the light path needs to go. Does this make sense? So imagine you're going from here to here and then here to here. So in air, light is going to travel a much bigger distance in the same amount of time as in water. And so water kind of bends towards the normal to compensate for the fact that the light is moving slower in that material. And it needs to do that in order to keep the frequency constant, in order to, for every wave crest that appears here, one leaves right there. So your light also gives another description for why this happens. Some people like to use some analogies for this. Like if you're driving a car in air, and this is one way for people to remember it, and then you're all of a sudden going into some mud or something where it's harder to move in, your wheel will start to turn. This side of the car will hit right here and turn, and then this side will just kind of sweep around and it will bend you towards the normal. That's being maybe a little too liberal with the analogy, and maybe that's just a mnemonic for remembering this. Really, you'd have to look at wave crests and force the frequencies to be constant to see maybe why it bends. By the way, this is the path that. So pretend that black line wasn't there. If you just started at this point and you wanted to get to this point, you said, well, and you have a couple rules for how fast light travels in both these things. And you said, well, what path can light take to minimize the amount of time to get from one point to another? It's exactly this path. So this is also the path that minimizes the amount of time spent that light would take to go from one to another. If it was a straight line path, the light would spend a little bit less time in air and a little bit more time in water, the distance in water would be greater, but it moves slower in water, so it doesn't want to do that. It doesn't want to travel that path. Imagine you could, imagine this is a beach right here and water, and you could run faster on the beach than in water. Maybe that doesn't make sense. Maybe this is land and water, and you could run faster on land than water. You needed to get from point 1 to point 2. You would probably run close to the edge right here before you had to swim, and you couldn't swim as fast. So it kind of makes sense that way as well. I'm just getting rid of this to clean up the diagram a little bit. Okay, so one last thing is to solve this problem right here. So really this is a Snell's law problem in disguise. Now the only warning here is that the angle that we're seeking is not the angle with respect to the normal. So notice how the light that just enters this, it's entering the water, and so you would draw the normal direction, and that's what we're going to do down here. So we're going to address the original problem. So we have water right there. We have the light ray, which I guess was orange. The light ray was coming in. So imagine this is really supposed to be just be the edge of the pool. So maybe I should draw it like right here. But really it's going from air into water right there. So the normal direction is not what we're seeking in the answer. So we're seeking this angle right here. So I'm going to label it with something else. I'm not going to call it theta. Why don't I call it phi? So this angle right here is going to be phi. And then this is the angle that we want. This is our answer. This is going to be the minimum angle of sunlight that gets through. Now from the geometry of the problem, we're told, so the light is going to refract. It's going to bend towards the normal because we're going from air into water. And we're told in the problem that we're basically told what the angle of refraction is, because we're told that in this pool, this side length is A and this side length is A. So notice that this triangle right here, and maybe I didn't do it justice right here, but this should be a 45 degree triangle. So the angle of refraction right here is 45 degrees. So from that we can get the angle of incidence, which is phi right here. So phi is the angle of incidence in this problem. And knowing the indices of refraction of air and water, and knowing the angle of refraction, we can solve for the angle of incidence using Snell's law. Okay? So, Snell's law tells us, from Snell, n1 sine phi is equal to n2 sine of 45 degrees. n1 is 1, it's air that we're coming from, and we're going to water. And sine of 45 degrees is 1 over square root of 2. Square root of 2 over 2 is the same thing as 1 over root 2. So phi is the arc sine of this, which is 70.1 degrees. So the answer to our problem, which was theta min, this right here, theta min is going to be 90 degrees minus this. It's the complement of our angle phi. Remember the angle with respect to the interface rather than the angle with respect to the normal, because overall these are 90 degrees with respect to one another. That's defining the normal direction. This is going to be 19.9 degrees. And it looks like that's our answer. So the main points of this video, angle of reflection is equal to angle of incidence for a smooth surface. For refraction, you need to use Snell's law and make sure that the angles are with respect to the normal direction. Those are the key things. Okay. We'll get to, so this is only halfway through this section, by the way. We're going to get to total internal reflection in the next video. So I'll talk about that in another video. Bye.